lecture 7. Welcome to Analysis 1A, lecture 7. Last class we finished everything about limits. This class we're going to talk about limits for just a few minutes and then move on to doing like real stuff. So what I think we ended last class. I think I challenged you with a proof. Did I put on deadline that you should do this? I think I did, right? Yeah. So there is a theorem, and the theorem goes like this. That if the limit as x approaches a of some function is L, and the limit as x approaches a of some other function g does not exist, then the limit of the product cannot exist. And I like this theorem. It's a good example of something which is sort of it's not totally obvious how to prove this, but it's also not really that hard once you get down to doing it. It's more an understanding of how to write proofs and how to structure your thinking than it is like math per se. So all right, how'd you guys do on this? Feedback from class.
Not good.
Not good. Okay, cool. Gayhard, did you get anything? Ethan Chen got something. Ethan Chen.
Should I just say what I wrote?
Yeah, I guess.
Like I thought, so that's what we're trying to prove. So then, let's just assume that f of x times g of x exists.
Oh, classic move.
Yeah, just like
Note that pretty much for the rest of your life, anytime anyone asks you to prove a statement and the word "not" appears somewhere in that statement, then it's pretty much going to dictate what kind of proof it's going to be. If I'm trying to prove that some limit does not exist, then the straightforward way to do that is to suppose that it does exist and then to get a contradiction. Is everyone kind of cool with that? Or maybe you thought that already, or maybe you didn't. So what Ethan Chen says to do is to assume that the limit as x approaches a of f of x, g of x exists, and let's just say that is that what you just did?
Yeah, right, exists.
Exists, okay. Assume that this limit exists, and then if somehow that leads to a contradiction, well, then I can conclude that it does not exist, and then it'll be done, right? Yeah? Okay. Okay, keep going.
And we also assume that the limit as x approaches a of f of x is some L not equal to 0.
Yeah, I did that over here. Oh yeah, that's kind of important. That this limit, not only that this limit is L, but that L is I think I said positive, right? But all that really matters is that L is not 0. Yeah, because as we've seen, 0 times does not exist. Different things can happen. But if the limit, thank you for correcting me there. Yeah, the limit is x approaches f. It needs to be some so-called normal healthy number. If that's L and this limit does not exist, then okay. So.
And then we know that the limit of g of x, which is basically the limit of f of x times g of x over f of x, like we multiply by f of x over f of x, exists. So g of x must exist if both f of x times g of x and f of x exist.
Yeah, this is actually pretty much just like a one-line proof. In fact, it might be simple if we say this, we might as well just give it like a name, right? Let's just say, because the limit's a number after all. So if this limit exists, then let's just say that the limit is k, where k is some number. And then he says, well, look, we'll take this limit, which is the limit as x approaches a of g of x. This limit is supposed to not exist, right? But he says the limit as x approaches a of g of x is pretty much just the limit as x approaches a of f of x, g of x over f of x. That's kind of what you're talking about, right? And then we can use a limit law that says like the limit of a quotient is the quotient of the limits. So this is the limit as x goes to a of f of x, g of x over the limit as x goes to a of f of x. See what's going on here? And this numerator is k, and the denominator is L. And so what have I just showed about the limit as x approaches a of g? Yeah, this is a major contradiction, right? We just showed that the limit as x approaches a of g of x exists. But that's a contradiction because we assume that it didn't exist. I mean, I don't know. You guys don't seem impressed. Yo.
This is like jumping away from this, but can't you do it like another way?
I don't know. This seems okay. Like what?
Like if you say that if you like rederive what d and e actually means, and say that the limit as x goes to a minus of g of x is some number k, and the limit as x goes to a plus of g of x is like m.
Yeah, but that assumes that particular kind of does not exist thing, right? That assumes that g has like a jump discontinuity.
Or like
that's just one of the.
I mean, it could be like infinity, like.
Right,
We're
or
assuming that-
oscillating, or could be, who knows, could be all kinds of weird things going on, right? Yeah, this is the most, I mean, actually, if you just say this in words, it kind of just makes complete sense, right? If the limit as x approaches a of f exists, and the limit as x approaches g doesn't, then the limit of the product can't exist, because if the limit of the product did exist, well, then you could just divide by f, and you just get g, and it would exist. I mean, that's basically the proof in words. Calvin's cool? Okay, cool. If Calvin's cool, I'm cool. Move on. We move on. There was some bookwork.
Yes.
It was pretty short and easy. Should we go over it for like 1 minute?
No.
Can we do like
We can do like one problem. Or
79?
which one?
79.
79.
Doesn't this delete the possibility that the limit of f of x, g of x is like infinity?
Yeah, but I'm including that under the rubric of does not exist. Yeah. So.
Very good, but sure.
Oh yeah, I see what you're saying over there, Rabbi Husband. Okay. So this was from section. Our book kind of weirdly put infinite limits like way ahead in a whole nother section.
Yep.
What problem are you guys talking about? 79? Oh yeah. This problem's a little bit exciting. Actually, should we do a couple of these? No, maybe just that one. This problem, kind of awesome. It says graph the function f of x equals x cubed over root x squared minus 4. Alright, so this is exactly the kind of function which is too hard for pre-calculus students, so I wouldn't give you a function like this. But now that we know limits, which we kind of knew all along, but now we've sort of formally investigated it, and we have the language to describe these kinds of things, then I think we can now do this. Although it's mostly pre-calculus, it's really barely any calculus here. And this is supposed to get you kind of involved with discussing asymptotes and using the formal definition of asymptotes. So all right, let's talk about it. Facts about this function. Calvin, give me a fact.
Cannot exist at 2 or negative 2.
Yeah. So x cannot be 2 and x can not be negative 2. More.
Absolutely.
Yes, I mean.
X has to be greater than 2 or less than negative.
Yeah, Calvin, not just that it can't be 2 or negative 2, but I can't plug in like 1.5 either, right?
Yeah.
Or 1 or a half or anything like that, right? In general, x squared minus 4 must be greater than or equal to 0. And in fact, it can't be equal to 0. It has to be greater than 0. So x squared has to be greater than 4. So Samin says that, in fact, the domain of this function is everything from negative infinity to negative 2, open, and from 2 to infinity, like that, right? Okay, so that's important. Domain issue. More things. Redden.
If you take the limit of f of x as x goes to infinity, the limit is infinity. And if you like keep on doing it, then you find out that as x approaches infinity, f of x approaches x squared.
Yeah, he's doing the cool one now. The cool one, so he said a whole bunch of things that were all true, which is that the limit as x goes to infinity of this function, well, that's just going to be infinity. That's pretty clear, right? Because the top is basically like a cubic and the bottom is more or less like root x squared. But not only does this limit go to infinity, he says, but also, as we might ask the question, how does it go to infinity, like we did when we graphed rational functions. So as x approaches infinity, this 4 is becoming more and more irrelevant, right? And as this 4 becomes more and more irrelevant, this bottom is basically like root x squared, which is x when x is positive. So So can I just say, like, you know, x, I'm being a little bit informal now, but this is going to be looking more and more like x cubed over root x squared, which, since x is positive, is basically like x cubed over x. You guys see what he's talking about? Yeah, so this is actually an awesome thing that never came up in pre-calc C, although some years people ask this question, like, hey, we have slant asymptotes, can we have like parabolic asymptotes? Answer, yeah, here's one right here, right? This function is going to be looking more and more like the parabola y equals x squared as x goes to infinity. And while we're at it, let's do the negative case. As x goes to negative infinity, what's happening? Yeah, now we just have to kind of be careful about the signs and stuff, right? This is going to be x cubed over, well, I'll just do it out, right? So x cubed over root x squared minus 4 is now looking a lot like x cubed over root x squared. But root x squared when x is negative is actually negative x, right? I guess you gotta get shy all the time. So this is negative x squared. Yeah, so when x is a huge negative, you plug in like a million, you're gonna square it. And
X squared.
did I do that right?
Negative.
I feel like I did.
Yeah.
Yeah, I mean, and also just to common sense it out, right? Plug in negative a million, then you're gonna get you cool?
Yeah.
Or let's plug in a really big number like negative 10. If I plug in negative 10 on the top, I'm gonna get negative 1,000. On the bottom, I'm gonna get negative 10 to negative 10 to 100 square root of that 10. So it's gonna be negative, right? It's gonna be fun. Okay, so that's cool. More things. Obviously, there's just a couple more little things to deal with. Maybe you guys think they're obvious. I don't know. What's other facts? Try to use the word asymptote in your answer. Oh, what's going on? You guys make me call him Emma. Emma.
There's an asymptote at x equals 2 and x equals 2.
Yeah, why?
Because over 0. Like it gets really, that bottom thing gets
Yeah,
really
can I get like
small.
can I get like a very specific statement though? Can you give me
Okay,
the precise limit which
the
justifies
limit
that?
The limit of f of x as x goes to 2 is infinity.
Someone fix that statement. It's not quite exactly right.
2 plus.
2 plus. Yeah, this is the kind of thing I expect you to be able to do, right? To cite the appropriate limit, and the appropriate limit here is the limit as x approaches 2 plus of x cubed over root x squared minus 4. Well, what is that? It's the top is basically just 8, and the bottom is going to be a little bit more than 2 squared is going to be a little bit more than 4. Minus 4 is going to be a tiny positive. Square root of that is a tiny positive. So that's going to infinity. Everyone okay with that? You need to write that limit, and then you need to say something like, so what? Yes, so there's a vertical asymptote at x equals 2. That's just the definition of vertical asymptote. That as x approaches 2 from either the left or the right, that the function goes to either infinity or negative infinity. Okay, and then somebody new, Shivani, give me the other one.
The limit as x goes to 2
Negative 2 minus, yeah. Right, because as we saw, the function's undefined between negative 2 and 2, so I have to look at what's happening on the other side of negative 2. Now, what do I get at the top, basically? Pretty much negative 8. And then down here, if I take a number a little bit less than negative 2, that's like negative 2.1 squared, a little bit more than 4. So then this is like a 0 positive, right? Is everyone cool with this? Ron, you cool?
Yeah.
Yeah, so this is negative infinity, and so by the definition of vertical asymptote, since I showed that the limit as x approaches negative 2 minus is negative infinity, that there is a vertical asymptote at x equals negative 2. All right, I think I'm ready to put this all together. It's a pretty cool function. Let's see. There is a vertical asymptote at 2, another vertical asymptote at negative 2, and then, this is the birthday present, we have parabolic asymptotes. And then I guess I have to do this one too, right? Okay. So, and then I guess the only root is at 0, so I can put a dot here. No root at 0. 0 is not part of the domain. Almost made a mistake, Brandon. Alright, so now probably maybe like a sign chart is a good idea for this. What's the sign chart? Where's the change sign? It's kind of a weird trick question. I would just say it changes sign at 0. The denominator is always positive, so only the numerator. But though it changes sign at 0, it's only, so maybe the sign chart looks like this. Negative, no, positive, something like that. Alright, so cool, so what does the graph look like? Well, you just read it off of your investigations. As x approaches infinity, it's going to be looking more and more like a parabola, and then shunk. And then down here, yeah, this is terrible scale. And then it's going to jump. Yeah, the true, we should zoom out. If we zoom out,
What? I think it's so much.
why are you laughing? My crappy picture.
Yeah. Yes.
It's going to look a lot like a parabola, and then so suddenly we get to 2, it's going to jump. It's going to kind of look like this. Yeah, that's better.
Okay.
Cool. Okay. That was pretty fun. Let's do maybe like one more problem. Let's do like one more. Pick one more from this section.
43.
43. Yeah, f of x equals root or absolute value x over x plus 1. I'll just kind of squeeze this in over here in the corner. Are you getting all this?
Yeah.
F of x equals absolute value x over x plus 1. That was the problem, right? This is another thing which is technically a pre-calculus student could do this, but it's sort of hard. Well, it's not that hard really. So I think the problem said investigate all asymptotes of this function essentially, right? Is that what it said? Something like that. Okay, Alice, explain. Kind of just do a bunch of limits. I think we should do 4 of them. Yeah, we take the limit as x approaches -1. Maybe we'll first do the -1 from the right, and then we'll take the limit as x approaches -1 from the left. So if we take the limit as x approaches -1 from the right, then the top is basically just 1, right? So the top is basically 1. And the bottom is, if I'm a little bit more than -1, it means I'm like -0.9. So that's going to be a tiny negative. So that's negative infinity. Right? And the limit as x approaches -1 from the left. Did I do something wrong? -1 plus. Oh, yeah. Oops. -1 plus. So -0.9 plus 1 is like a tiny positive. Yep. You were all correct. And over here now, -1 minus, so that's like -1.1, so it's a tiny negative. So this is still 1 over a tiny negative, so that's like negative infinity. Okay, so that together, these two, actually I really only need one of them. Together these two imply that there's a vertical asymptote at x equals -1. Good so far? Okay, and now we just limit as x approaches infinity and negative infinity basically, right? So what is, kind of squeezing this in here on this side of the board, what is the limit as x approaches infinity of this function? Say it loud. Yeah, it is 1. It is 1 because as x approaches infinity, x I can say for sure is definitely positive, right? So this is just the limit as x approaches infinity of x over x plus 1, and that's just 1. But if I take the limit as x approaches negative infinity of absolute value x over x plus 1, well now x is like -1,000,000. So well, since it's negative, then this is the limit as x approaches negative infinity of negative x over x plus 1. And so this is -1. Is that what you guys got? So if you're going to graph this, this would be kind of a cool function to graph. it would be 1,
But yeah.
-1, and then it'll be 0 at 0, and then at -1 there'll be an asymptote. And what does the actual function look like? I guess, did we grab something like this before? No, I didn't.
Nope.
Wait, the other, you're missing the asymptote.
Where?
Oh, wait, no.
No, I think that's it, right?
Do you want to say pluses and minuses for the one? Because like,
Yeah, maybe I care about that, right? That it's, as x goes to infinity, it's going to be a little bit less than 1. So I think it's going to kind of look like that, right? And then as I get close to -1 from the right, it's going to go to infinity. Yeah, so something weird like this is going to happen, right? Yeah. And then to the left of -1, it's going to be negative infinity. It's going to look like this. Perhaps crossing that asymptote, does that ever happen?
that's negative.
It does or doesn't?
Yeah, because negative x over x plus 1.
Yeah. Negative x over x plus 1 is -1 minus 1 over x plus 1. So no, it won't cross.
Is it -1/2?
Is there something wrong? -1/2? What? I feel like this is right. What's wrong?
No, like where it crosses.
Oh, I mean this point. Yeah, it definitely crosses here. He says it crosses at -1/2. Yeah, I agree. Because, wait, -1/2.
Yeah.
Does that make sense?
Yeah.
Yeah, -1/2 over 1/2. Oh, but I'm supposed to be here, right? So yeah, if you plug in -1/2, you get 1/2 over 1/2. Yup. Yeah, so I'll have this point -1/2, comma 1. Anyway, kind of cool. This was like the last problem from the, wait, so what happened? You guys were supposed to do the pages like 1 through 4 or something, or 1 through 5 of the review packet? 1 through 5, okay, so you still have some left. Yeah, the last page of the review packet, some of you, I don't know, maybe you just did the whole thing, is a problem kind of like this that makes you get into this whole thing. All right, how are you feeling about limits? Can I have this homework? That was like way too long. Let's make a pile over here by my sandwich. I don't need the
You don't need to.
Also, let's, yeah, what's up? Yeah, could you, yeah. And also, Shivani or Al, somebody, see that giant pile of papers? Can we pass that back? I meant to do it at the beginning. If I don't do that in general, you should just like do that. You should remind me. While they are doing that, can we go over, let's take about 10 minutes, maybe, and let's go over some aspects of the review packet. How does that sound? How did the, yeah, we're gonna go over there. How did the review packet go? Eh? All right.
Well, wait, Mr. Rose,
What's up?
do you have a spare one that I can look at for
Oh
now?
my God.
I left it at home. Don't worry.
Okay, not worried.
It's all good.
Calvin.
Thank you.
So let's go over some of these. Number 1, limit as x goes. Well, let's just, I don't know. What should we do? Let's just do a couple. So the limit as x goes to 0 of arctan -e to the -x. How do I do this? Maybe I make a little graph of -e to the -x off to the side. It's like normally the x but flipped over the x and also flipped over the x-axis. So I guess this looks like this, right?
Yeah.
Yeah. Yeah. So, but actually it's kind of like not as to scale as I want it. So let's maybe do it like that. Yeah. So that's -1. So the limit as x approaches, oh, so this is really just -1? Is this just arctan -1?
Yep.
Yeah, this is really just arctan -1. Says the man who's doing the packet right now as we go. So did you guys get -5 before? All right. What about the limit as x goes to infinity of arctan negative e to the negative x. Well, now as x goes to infinity, this is pretty much approaching like 0, right? So is this just 0? I think it's just 0. These are kind of boring. And the last one is the limit as x approaches negative infinity. Well, as I approach negative infinity, then the inside of the arctan, so this is the limit as x approaches negative infinity of arctan negative e to the negative x. If this inside is negative infinity, then arctan negative infinity is like negative pi over 2. Yeah? Okay. Number 2, the smart way to do it is just to apply a log rule and just bring that 3x squared down and then just cancels, and the answer is just 12. For number 3, it's just straight up from the notes, like rederived. Let's see, what else? Oh, let's do this epsilon delta proof. We did probably, if my memory serves me correctly, it's like we did 1 epsilon delta proof in class, and I assigned maybe, what, 1 for homework, and we never went over it? That's probably about right. There's going to be an epsilon delta proof on the test. It is going to be
Hard.
no, it's going to be easy, because we only really did easy ones with lines, right? So it's like 3 points. So let's maybe just review this whole thing, 'cause it's been 2 weeks. The limit as x approaches negative 5 of 3/5 x minus 4 equals negative 7. All right, I do have high expectations though. I expect you to go through the whole business. So let's make a graph of this. Let's see, I'm approaching negative 5, right? And the answer is negative 7. So I'll do something like this, 2, 3, 4, 5. So there's negative 5, 2, 3, 4, 5, 6, 7. And we'll pretty much be over here. Alright, and then when I plug in 0, I get negative 4. So I say this function, this line, looks pretty much like this. Are we cool with that? Okay. And I have this point, bam, good enough. Negative 5, comma, negative 7. Alright, so what is it that I really mean when I say the limit as x approaches negative 5 of this function is negative 7? Well, I mean that the y values are getting closer and closer to negative 7. How close? As close as you want. And so what is happening is that somebody challenges me with an epsilon, and here I put in some negative numbers just to see if you would freak out. So epsilon represents how far away from negative 7 I am being challenged to be. And yes, I expect you to have a graph on your paper that's like labeled and like blah blah. And then what do I do in response to this epsilon challenge? In response to this epsilon challenge, I have to find a delta. And delta represents how far away from negative 5 I'm allowed to be. Delta is, yeah, it's an interval around negative 5. Okay, and then what I would like you to write out is the actual thing that I'm trying to prove. And the actual thing I'm trying to prove is, well, just like I said, but now kind of in mathematical language, that for all epsilon greater than 0, there exists a delta greater than 0, such that, in other words, no matter how tiny of an epsilon you give me, I can find some delta, such that as long as I hang out pretty close to negative 5, my outputs will stay pretty close to negative 7. So and you can do it however you want. You can write it the kind of commonsensical ways to say, well, if x is somewhere between negative 5 minus delta and negative 5 plus delta, x not equal to negative 5, then my function must be somewhere between negative 7 minus epsilon and negative 7 plus epsilon. Cool? Alright, the slightly fancy way of writing it with absolute values, it's a little bit less obvious what's being discussed, but it's like much easier to work with. Instead of saying this, I can say, well, the distance between x and negative 5 is less than delta. That's just another way of saying the same thing. If that's true, then the distance between my function and negative 7 is less than epsilon. So I'll just treat it, I'll just use this one because it's easier, but you can really do either one. All right, so this is what I have to prove. How do I prove this? Well, someone's going to give me an epsilon, I have to respond with a delta. Some new person might give me some new epsilon, I have to respond with a new delta. What I want to do to actually prove that this is true is show that for any possible epsilon there's a delta. Delta is going to depend on epsilon, and so I must discover the secret formula which enables me to provide a delta for any epsilon. So I'm forcing you to do this even though you might think it's kind of obvious. So what we do is a discovery phase. And in the discovery phase, we try to discover the epsilon that works. Or the delta that works, and in the discovery phase, we're just going to start with the thing that we're trying to prove. So I just begin with f of x minus absolute value of 7 being less than epsilon. So I start with my y value between the parallel lines, and now I'll discover which x values make that true. And so, okay, so we can just do this. There's a bunch of ways to do this. I don't know. Well, I guess, what should we do?
Bring out f of x as the actual.
Yeah, plug in, Calvin says plug in the actual function. 3/5 x minus 4, that's plus 7 is less than epsilon. And so this says 3/5 x plus 3, absolute value is less than epsilon. Okay, now what?
Get rid of the absolute value by putting it so it's greater than negative epsilon and less than epsilon.
Yeah, I could do that. I can do that if you want me to.
Yeah.
So 3/5 x plus 3 is between negative epsilon and positive epsilon. Now I guess, like, now what?
Subtract 3.
Subtract 3, yeah. So negative 3 minus epsilon is less than 3/5 x is less than negative 3 plus epsilon. And then finally, multiply by 5/3. So if I multiply by 5/3, let's see what happens. So I get negative 5 minus 5/3 epsilon is less than x. Is that right? Mm-hmm. Which is less than negative 5 plus 5/3 epsilon. Yeah, this way's a little uglier, but in some ways it's just so much better because there's just more thinking involved. Because now what I've shown is precisely the kinds of x values which satisfy this inequality. It's whenever I am between negative 5 minus 5/3 epsilon and negative 5 plus 5/3 epsilon. And so, given this statement, it's pretty clear that 5/3 epsilon is how far away I'm allowed to go, right? So the conclusion of discovery phase is that we set delta to be 5/3 epsilon. All right, now that we have discovered the delta that works, then we can just, now we have to do the proof. So here comes the proof. So we write something like proof begins here, proof begins here. And in the actual proof, I'm challenged with some epsilon. So